Hello fellow problem solvers, so they're already doing a problem from the Irish Math Olympiad 2018 paper 1 problem number 3. I suggest you try this decent algebraic problem out for a minimum of 15 minutes, ideally 30 to 45 minutes, not more than an hour and a half. If you'd like to go along with us, I suggest you give this a go for the next 15 minutes. So now let's begin. What is this? So let's find out functions, quadratic functions such that f of 1 is f of negative 1 is f of 0. So how are we going to approach this problem? Well, one way is to say, okay, I know what f of 0 is c, this is a minus b plus c, this is a plus b plus c, and then I'll f that, and I'll get an expression of a quadratic degree in a, b, and c, and then, I'll deal with it. Right? That's one way you can go about it. Another way to go about it, which is what we'll do, is, let's look at what is a quadratic expression. What is this quadratic thing? Well, it's like when you have a graph like this. There are a bunch of things actually we could say about this problem. One is that we could look at if f is a solution, is something else also a solution? For example, if f is a solution, is f times k a solution as well? And the answer here is, well, f of 1, it's like f times k, everything inside is multiplied by k. And then when you f again, you have then effectively, I'm curious actually, if f times k is g, right, f of x times k is g of x, then g of x is equal to g of f of x times k is equal to, so g of this is equal to f of what's inside, so it's f of x times k times k. Now the things that are inside get multiplied through, it's I think it's questionable whether or not the same thing holds true. So maybe this doesn't work out. So maybe we can't multiply. Can we add something? If f of x plus some d is equal to g of x, what do we then get as g of x? Again, there's some question like we would get g of x would be g of f of x plus what's it called, d. And then this thing right here would be f of x plus d plus d. It's questionable whether the same thing would hold true. So we test these out and we see they don't work. Why did I do this? It's a pattern. You want to see if f works like you can. Does some f times plus or minus something also work? Because then maybe you will be able to assume some things that can make the calculations easier. That's basically the idea behind assuming this. And it's one of the patterns that you see in algebra. So now, but I want to talk about a quadratic function. What does it look like on a graph? On a graph, y is equal to f of x. Right, this is the x, y coordinates. And the answer is it looks something like this, right? These are the two zeros. This is, of course, if a is bigger than 0. Otherwise, it's a frowning face. So this is what a quadratic function looks like. And now, what do you have? You have f of something is f of something is f of something. Now you could look at f of x, which is a degree 4 equation, and that will give you a messy thing. But we don't need to do that. We need to look at, what does this mean? It's like a little bit of a tricky question, like what does this mean? Like what do I mean? What does this mean? I mean, you have f of a, f of some x1 is f of x2 is f of x3. Can that be the case? And the answer is, if f of something is f of something else, is f of something else. Like if we have, this is say f of minus 1, say it's here. We don't know where it is. This is not meant to be minus 1. Say f of minus 1 is here. f of 0 can either be this point, or it can be points such like that, where we have this value, or it can be this other. So it can be either this point or this point. F of 1 needs to be between one of these 2 points, because we have f of some x is f of y is f of z. So either we have y is equal to z, y is equal to x, or x is equal to z. Or all three might equal true. And why do I do it this way? Because it simplifies our casework. Right? We have, this is equivalent to f of a plus b plus c is equal to f of c is equal to f of a minus b plus c. That's what all these values give us. And now, given this is how a quadratic equation looks like, we can either have f of c, like c is equal to a minus b plus c, c is equal to a plus b plus c, or a plus b plus c is equal to a minus b plus c. Okay? So that's the first thing. Another thing is, what do we also know about these two values? If these two things are separate? Well, if they're not equal, we know their sum is here at the bottom of the, sort of at the minimum of the functional equation. We know this from Vieta's rules. And this sum, what happens when you, instead of c, you add d? The functional equation moves up or down if d is positive or negative. But what doesn't change is this thing, like what point, for what x, this is minimal. That's the thing that doesn't change. And I think that is the x equal to, so what is this? This is, one way to look at this is a times x squared plus b over a plus c over a, b over ax plus c over a, which is a times x plus, so if it's b over a, b over 2a squared, so that I get this plus something. So for x equal to minus b over 2a, we will get this minimum. And how we get this is this plus this over 2. So we get the solutions to these like this is how you get also Vieta's rules. But this is just another way of looking at this. So we know that either they're all equal, or their sum, which is, mind you, independent of c, like they could all be equal to some number 5. And if they have if they're 5 at 2 different places, that would imply that their sum is equal to b over 2a. Right? It's not just for the zeros, it's for anything, 2 things that are equal. And now, with this, we can look at casework. For example, we can say we have these 3 things, right? And 2 of them must map to the same thing. Must be either this thing or this thing. Right? Say this is f of minus 1, then f of 0 is either this or this, f of 1 is either this or this. So 2 of them are at the same point. So we can go by looking at different caseworks. What if, say, the first case is that a plus b plus c is equal to c. In other words, b is equal to negative a. And then what do we know about the last one? Now we know that these 2 are equal. If b is equal to negative a, then the functional equation looks like ax squared minus ax plus c. This is what the function looks like. And now for f of 1 and f of 0 are both equal to c. And then f of that will also be equal. But what is f of negative 1? Well, f of negative 1 is going to equal what? It's going to be ax plus c. So 2a plus c. And we plug in x is equal to negative 1. And now we have f of 2a plus c is equal to f of c for this quadratic equation. Now what do we do? The answer is, well, we can equalize the 2, or we can also say like, wait, there's 2 things that could be true. Either these 2 are the same thing, like internally, f of something is f of something else. Either they're the same points, or they sum up to, what's it called, minus b over a. So here, we have either they're the same points, which is impossible, because then 2a plus c would be equal to c, which would imply a is 0. We can't have that because it's a quadratic equation. A is not equal to 0. So we have that these two things must sum up to, so 2a plus 2c must sum up to what is minus b over a. But given that b over a is, what's it called? We have ab is equal to minus b over a is equal to minus a over a is equal to 1. So we have a plus c must be equal to 1. And now what does this give us? This gives us that the equation, mind you, this just means c is equal to, actually 1 over half, 1 over 2. This means that c is equal to a half minus a. So the functional equation is f of x, ax squared minus, what's it called, ax, plus a half minus a. Okay? Now let's, just to be doubly sure, check that we haven't made any algebraic mistake here. And we have now, when we check 0, f of 0 is going to be, so this is 0, 0, a half. And then f of a half is going to be, okay, so this is going to be 0 for the half. And actually, no, this is going to be a half minus a, my bad. So a half, we get 1/4 of a, f of 1 over 2 is 1/4 a minus a over 2 plus a half minus a. So this gives us a fourth minus a half, which is minus 1 over 4a, plus this minus a, so it's a half minus 5 over 4a. This is what f of 0 is equal to. F of 1, so it's going to equal to 1 minus, like a minus a is a, it's going to give us 1 over half a. Actually, wait a second. F of 0 didn't give us a half, it gave us a half minus a. It gave us f of a half minus a. And that's what f of 1 is also. F of 1 is also half minus a. And so from here, f of this is what we're actually looking to see, is going to be, so it's a times a half minus a, because this is x squared minus, what's it called? X minus x, ax times x minus 1. So this is a half minus a, so it's a minus a half minus a plus 1 over 2 minus a. So that's what we have. F of 1 is equal to this, and this is also f of 0. And now f of negative 1, which is the interesting one, the different one, which is the thing that gave us the a and c, is going to equal what? F of negative 1 is going to equal a, what's it called? Negative 1, so 1 plus 1, 2a minus a is, it gives us an a plus a half, right? This is 2a minus a plus a half. And now, when I sum these two, I should get, I'm getting a 1, which is what I should be getting. And now when I do this is a times a plus a half, then x minus 1, a minus a half, and I have plus 1 over 2 minus a. Now this thing feels a bit wrong, but actually it's not, because if I take out the minus here and the minus here, I'll get this is equals this, so we're good. So this is one of our solutions. And we got that solution by asking like by saying the first case is f of 1 is f of 0. And now we need to look at the other two cases. I invite you here to pause for another 10 to 15 minutes to try to push the problem further. And here's the next case. So we have f of 0 is f of negative 1. What does that give us? Well, it gives us f of 0, f of negative 1. These two things are equal, which gives us that a minus b is equal to 0. In other words, a is equal to b. And then our function equation is f of x is ax squared plus ax plus c. Which also makes sense because this is like the roots here, like these two, like this needs to be equal for 0 and negative 1. So now we have that, what's it called? We have a is equal to b, so f of 0 is f of negative 1. And then we know f of 1 is going to, and we know that f of 0 and f of 1 is going to be, what's it called, equal to c. And f of 1 is going to be 2a plus c. And now, these two things, can f of 1 is equal to f of 0. This implies that f of 2a plus c is equal to f of c. Again, if these were the same solution, then we would have a is equal to 0, which we know we can't. So they must sum up to the minimum. What is the minimum? B minus b over a, which is minus 1. So we have 2a plus 2c is equal to minus 1. In other words, c is equal to minus 1 over 2 minus a. And then we have the functional equation is f of x is ax squared plus ax minus a half minus a. Now I'm thinking, is there something... I'm thinking like back to the original thing, like whether there was a thing to add or multiply, like maybe a way to get from one to the other, any without loss of generality we could have done, but I can't think of any. If you can think of some, please let me know. So now what do we have with this? Well, now we have, okay, then this has to be solution. Again, just double check our algebra. It says, and the algebra actually does work out. So we have now, we've checked that this is actually the case, and now we have our solution from this case. So now we have that if f of minus 1 is equal to f of 0, we have that the solution f of x is equal to ax squared plus ax minus a half minus a, right? That's what we got here. And now we need to move on to our third case. If you haven't tried the third, if you didn't do the third case, I invite you, just pause for 5 minutes. This helps you work on your algebra skills, thinking. It's just like a little technique building problem. And for the third case, and we see like we get what we just had beforehand. Now we have it's ax squared plus c. Now if these two things were to be equal, then we would have f of c is f of a plus c. Now if the two things are the same solution, then we would have what? We'd have c is equal to a plus c, which implies a is 0. That can't be true. And then finally, which means they must sum up to minus b over a, which is here is 0. So now we have that a plus c, so a plus 2c is equal to 0. In other words, c is equal to minus a over 2. And so the functional equation is f of x is a times x squared minus a half. I think this is just a nicer way to write it down. And now again, we double check our work and we get that this does actually check out. So we get that the three possible solutions. So the third case gives us the third case f of 1 is f of negative 1. Gives us that f of x is equal to ax squared. What did I have here? Minus a half minus a over 2. And so these are the functional equation, all functions of this form, which satisfy f of 1 is f of 0 is f of negative 1. And for any a that's not equal to 0. And this finishes up our problem. Now there's a couple of things I want to clear up. Why did I always change I always wrote things in terms of a, I wrote B in terms of A and C in terms of A instead of the other way around, right? I could have also wrote A in terms of B and C in terms of B. And the reason I did that is because I only have a condition for A, so it doesn't matter which one I choose. But like which one of these I choose, it's sort of like, I don't think it matters. But I have a condition for A, I don't have one for B and C. So it's easier to see here that, oh, A is non-zero is my only, like it's this is a solution with A non-zero. If I wrote this in terms of, say, in terms of B, actually I couldn't write this in terms of B because B is zero. But in terms of C, if I wrote it, I mean, I could still say C isn't equal to zero. But you know, I'm like here, it's a much simpler thing for every single one of these. And this sort of problem just illustrates like, sometimes these math problems, they have a solution where you just like, you know, go, just like brute force it. Like what would I have if this was equal to this? I have A plus B plus C squared times A plus B times A plus B plus C needs to equal to C squared A plus CB plus C. And now you do the algebra here, like you get this equation and you need to, really what you need to do is to factor this, right? Okay, CB cancels out, CB cancels out, C squared A will cancel out here as well. But after that, actually let's just like do this, just do this case, just to illustrate that there's a, I would find this more difficult. This is what? This is A plus B squared times A plus A times 2AC, A plus B, plus C squared A, which will cancel out, plus B times A plus B, actually just the C's here, A cancels out, this is equal to 0. Okay, now I have A plus B times A plus B, A plus 2AC plus, what's it called, B is equal to 0. Now either this is 0, A is equal to negative B, or this is 0. Like I would still need to have cases. It's just, why bother? And mind you, this is only because I saw I could immediately cancel out C, so factoring wasn't that difficult. But I think in general it would be a tad more difficult. Now, what does this equate? If this is 0, what does it imply? Can I factor this? This is A squared. I don't think I can factor this nicely. I think that's an issue here. I legitimately cannot factor this nicely. Because the 2AC is alone. That's actually kind of weird. Did I make a mistake somewhere? No, 2AC is alone. And yeah, like that, this is like more difficult to deal. Like when is this equal to, if this is 0 and then I need to combine all the other two equalities, it just feels a bit unnecessarily difficult. And I'd rather avoid it. The f of 1 is f of negative 1 is probably A minus B. Actually, if f of 1 is f of negative 1, I probably get to factor out the B, because B is equal to 0 in this case. But you see, like there's a lot of casework, and then I'd need to say like if none of these, if A plus B isn't 0, if B isn't 0, and if A minus B isn't 0, then I'd need to get a contradiction that all of these, like this one and the other three I would get, aren't all equal to 0. Like can't all equal 0 at the same time, and that just seems, maybe it's simple, maybe it's not. It seems to be more algebraic. It's also just, this feels smarter, right? It feels like I'm taking a little bit of a cheat code, right? I'm doing a little bit of thinking beforehand. Oh, quadratic. I can have only one thing, two solutions. They must sum up here, yada yada. And mind you, all this checking we did later, we don't need to do that. I just wanted to do that to illustrate that sometimes if you have the time, check your algebra. It can needlessly cost you a point. It once, for me, it once cost me a I had a shared first place instead of just me being a first at a competition, because I quickly wrote down that 20 plus 30 minus 1 is equal to 40. Right? I still think it might have been 49, but I wasn't there to complain about this. But see, algebra can cost you sometimes. And there's like examples on exams where this can also cost you. And this is why we check. And now we're finished with this problem. Nice problem for the Irish Math Olympiad. And as always, thanks for problem solving.